In this video, we're going to be looking at the first part of topic 15E, which is chromatography, and this is part of the IA2 chemistry course from Edexcel. So we're going to be looking at not only chromatography, but also mass spectra and how we can use these two things together and get very accurate relative atomic masses, how we can use RF values in paper chromatograms and thin layer chromatography, or TLC, and understand why different substances have different RF values, and then look a little bit at HPLC and GC in terms of being types of column chromatography and how they are using retention times to be able to identify substances. So what is chromatography? Well, chromatography is used to separate a mixture of individual components and be able to identify what those components are by looking at the distance that they travel up the paper or the chromatography plate. Because if it's TLC, it's not paper, but it's a plate of silica. And we'll look at that in a little bit more detail in just a minute. But the most important part is it's separating a mixture into individual components. Now, you may have done this back in IGCSE when you were talking specifically about ink or dye, so to separate out coloured components, but we can use it for things that do not have colour, and then we can use something to be able to develop them and we'll be able to see the spots. So mostly what we actually use it for is not so much with inks and dyes, but we use it to determine the purity of organic compounds. So in topic 20, you will look at organic synthesis. But what we know from a lot of these reactions is that not all of the reactants convert into products. And if we have some of our reactants or some side reactions happening, we get an impure substance. So chromatography can help us understand, do we have impurities, or is it the pure value or the pure molecule that we have? And we can detect the spots that don't have any colour either using a UV or using a developer known as ninhydrin. We're not going to go into a lot of detail about this, but it's essentially a spray that you can put onto the spots and they'll turn pink. So how do we carry out a very basic chromatography? Well, this is something you've seen back in GCSE, so this shouldn't be new to you. We've got some sort of glass container with a lid that's generally a beaker, and we have the lid to prevent any evaporation of the solvent. We don't want the solvent to be evaporating, we want it to be moving up the chromatography paper. We have the chromatography paper, which is usually a porous paper that's specially made for this. We have our baseline on that drawn in pencil, because if it's pen, then that could interfere with the chromatogram. We have our solvent, which is generally water, but sometimes it can be an organic solvent such as potentially ethanol, but most of the time we will use water. And when we put our solvent in, notice that it stays below the baseline. We do not want it to go above the baseline, or else the spot won't move the way we want it to. And the spot of the mixture that we want to separate should go right in the centre of the baseline. Once you put it into the solvent will then travel up the paper and it will eventually stop when you take the paper out, and that where it stops is known as the solvent front. And then you can see now that we've got the separation of the components. In this case, we've got 3 different spots, and we will be able to calculate a value known as the retention factor to determine what these spots are. And we'll look at the RF value in just a little bit. Now, what we need to understand is that all uses of chromatography depend on something known as a mobile phase and a stationary phase. And you need to be able to know the difference between these two things and be able to define them. So the stationary phase is the solid or the liquid that does not move. So in this case, with our simple chromatography, this would be the paper. The mobile phase is a liquid, or sometimes it's a gas if it's gas chromatography, but for simple chromatography it's always a liquid that will move through the stationary phase and transports the components. So this would be the water or the solvent that travels up the paper. So the mobile phase is the one that's moving, the stationary phase is the one that stays still. If we have a component that is very strongly attracted to the stationary phase and very weakly attracted to the mobile phase, it does not move up the paper. It would rather stay in position being attracted to the stationary phase. If the opposite is true, so if the component is very strongly attracted to the mobile phase, it's more likely to move with the mobile phase as it travels up the paper, so your spot will travel further. So the retention factor, or the distance that it travels, depends on the affinity that a component has for the mobile phase or the stationary phase. Now, specifically for paper chromatography, as we said, the mobile phase is the solvent, and the stationary phase, whilst it is the paper, is actually the water that's trapped within the fibres of the paper. So we don't see that and we don't feel it, but there is water trapped between those fibres, and that acts as the stationary phase. If we've got thin layer chromatography, or also known as TLC, this is a very similar concept to paper chromatography. We just have a slightly different process. Rather than using paper, the stationary phase is a very thin sheet of glass that is coated with silica or alumina, not of alumina. So either silica or alumina, and this is a TLC plate here, and that's what we call it, where we've got this plate of glass with the silica or alumina on top of it, but the way that we carry out the chromatography is the same as paper chromatography. Now, when we're analysing the chromatogram after this process has been carried out, we do this by determining the distance that the component has moved, or the distance of the spot, relative to the distance of the solvent front, and this is known as the RF value, or retardation or retention factor. So to calculate it, we look at the distance of the component, and generally you look at the very centre of the spot of the component, and then we divide that by the distance of the solvent front. Now, this has no units because it is just simply a ratio of the two distances, and one other very important thing, it must always be less than 1, because the solvent front will always move further than the component. So if you get an RF value that is above 1, you've done something wrong and you should go back and check. And every component will have a specific RF value that we can then compare to. So you can do your chromatography, figure out your RF value, and then compare that to a reference standard. But what we need to make sure is that we take into account the fact that the values can change depending on what solvent we use. So if we are looking up a reference standard, we need to make sure that it is the standard for that particular solvent as well. Now we can move on to looking at a slightly different type of chromatography, and this is known as column chromatography. Now, the principles of column chromatography is the same as paper chromatography. The biggest difference is that we can use larger samples with column chromatography. So rather than just a spot of a mixture onto a piece of paper, we can use a tall column, and we'll look at a diagram to show what this looks like in just a moment. The stationary phase for column chromatography is again the silica or alumina, and this time it's packed into the column, and it's generally soaked in some sort of solvent. Again, the solvent can vary. The mixture that we want to separate is put onto the top of the stationary phase, so at the top of the column above the silica, we pour the mixture and we add some more solvent, and that solvent acts as the mobile phase. And when we open the tap, because it looks like a burette, we open the tap and the mixture will start to travel through the stationary phase along with the solvent passing it through, being the mobile phase, and then it will start to separate the component and we will get the different parts separating out. So we would get something that looks a little bit like this. So this is our packed silica, which is our stationary phase. And you can see that we have the tap here as well. And we add in our mixture plus some solvent, and the solvent is our mobile phase. And as it passes through the column, you can see that rather than having this green mixture, we're starting to separate into the blue and to the yellow. And the yellow is going to be more attracted to the mobile phase, because you can see that it moves through the column much quicker, whereas the blue is going to be more attracted to the stationary phase. because it moves through the column much slower, so it is more likely to be attracted to the particles of the silica. And eventually you will be able to have the yellow component come out and put that into a beaker or conical flask, and then put a new conical flask to collect the blue sample as well. So we're separating out the green mixture into a blue component and a yellow component because they have different affinities for these mobile and stationary phases. Now, if we just pivot slightly to looking at mass spectrometry, we've met mass spectrometry back in topic 2 and in topic 10, and we looked at it in terms of looking at just very basic abundance of the different fragments. What we want to look at now is how we can use high resolution mass spectrometry, or HRMS, to determine the molecular formula of a specific compound. And this is extremely accurate. So these spectrometers can give you a molecular mass to 4 or more decimal places. Because what you might find, if we don't use it very accurately, we can end up with compounds with the same molecular mass, and then we can't tell them apart unless we use something like infrared or NMR, which we will look at in the second half of this topic. So for example, if you have C4H10, C3H6O, and C2H6N2, if we were just to calculate each of those using our basic atomic masses, we would get an MR of 58. So we wouldn't be able to tell these apart. However, if we do it to 4 or more decimal places, we can actually see that there is a difference in the MR of these molecules, and then we can tell them apart. So to accurately determine the MR, we must use relative atomic masses that are also accurate to 4 decimal places. And the most common ones that you'll potentially use would be hydrogen, carbon, nitrogen, and oxygen. And you can see that these are compounds that you've met before and atomic masses that you've met before. However, they are much more accurate. So instead of 1, it's 1.0078. And it just allows you to be a little bit more accurate to determine the difference between the different molecules. So this will allow us to determine if the molecule is each of these 3, but it doesn't allow us to determine the structure. We need to look at the fragmentation for that, which we've looked at back in topic 10. So to look at an example, a compound is found to have an MR value of 84.0573. Which of these 2 structures could the compound have? Well, if we look at the first one, we can see that it is actually C6H12. So to figure out the MR, we're going to do 6 times 12.0000. Now, of course, 12 is the standard that everything else is measured from, which is why that is bang on 12 without any extra decimal points. And the 12 hydrogens is going to be 12 times 1.0078, and that gives us a mass of 84.0936. So that, of course, is not the correct answer, but let's just double check our second one, and we can see that that is C5H8O. So we get 5 times 12.0000 plus 8 times 1.0078 plus 1 times 15.9949, and when we add those together, we get 84.0573. So our compound is this structure here. So just looking at it in slightly more accuracy to be able to tell these 2 things apart. Again, this time we're looking at a high resolution mass spectrum, and you can see it only goes between 44.01 and 44.07, and we want to figure out what each of these would be. So when we calculate our masses using these accurate atomic masses, we find that the first one is 44.0624, Q is 44.0261, and R is 43.9898. Now, the 43.9898 doesn't even appear on this mass spectrum, so this one is not present. However, the propane and the ethanol are both present because those are the peaks that relate to 44.0624 and 44.0261. So again, just being slightly more accurate in terms of the values that we use. And we'll come back to looking at how mass spectrum works in conjunction with chromatography a little bit later on. So this is a new type of chromatography that we haven't met before, and it is known as HPLC, or high performance liquid chromatography. And it works very similar to the column chromatography, but it's just slightly more refined. So what you'll find is that all of this section would be contained typically within one unit, and you might have the computer display either on the unit built in or connected to an actual computer. And what happens is we've got our solvent reservoir, so we have a container of the solvent all the way present in there, and it passes through the pump and then comes into contact with the sample that is injected. And the sample and the solvent pass through the HPLC tube, and we get separation of our components. These are detected by a UV detector, and the results are then displayed onto the computer. So it's very similar to column chromatography, but there is just some slightly more refined parts. The main difference in comparison to column chromatography is column uses gravity. So the mixture and the components falling through the tube due to gravity. Because in our HPLC the tube is on its side, we can't use gravity, so we actually push it through using a high pressure. So that's the main difference. In terms of the stationary phase and the mobile phase, the stationary phase is generally silica. So you'll find either the column is packed with silica or there'll be silica coated on the inside of the tube, and that is a polar solid. And the mobile phase typically is hexane, however sometimes that can change depending on what type of mixture it is that you're separating, and that is a non-polar liquid. So again, our stationary phase being the solid, mobile phase being the liquid. So that's similar to the paper chromatography. The particle size of the stationary phase, however, in comparison to column, is much, much smaller. This gives us then much better separation of the components. This is why we call it high performance liquid chromatography, because it allows us to get much better separation of the components before we then detect them using our UV radiation. Now, the HPLC measures the retention time of the component in a mixture. And what we mean by this is it's very similar to the RF value that we found in paper chromatography. However, this time we are looking at how long it takes rather than the distance it travels. So the retention time is the time taken from the injection of the sample to the detection of the separated component. So we're measuring in terms of how long it takes to pass through the column, essentially. And the retention time will depend on the nature of the solvent that we use, the pressure that is used, and the temperature inside the column. So you'll find that these are usually specific settings that would be the same for the majority of samples, so that you can then refer to a reference or to a standard and be able to determine what the molecule is. So the second type of new chromatography that we need to look at is known as gas chromatography, and this is just simply another refinement of the column chromatography. The main difference to the previous one is that this is for gases, whereas HPLC is for liquids. So we have our carrier gas supply, and this is an inert gas that will act as our mobile phase. And we have everything else sort of contained inside this oven. So we have our sample being injected through the injection port, and then it passes into this coiled column. We need the column to be quite long to allow for the gases to separate, because of course, if they're in the oven, the gases are going to move faster and the particles are going to be randomly moving. That's just the nature of a gas. So we have this column being coiled to give us more and more distance for them to travel, so that we get better separation. So they'll pass through the column that will be coated with the stationary phase, and depending on their affinity for the stationary phase and the mobile phase, we will get a separation. once the gases or the different components are then passed into the detector, they'll be passed through to the data system or the recorder to determine which component it is. So, as I said, the metal tube is generally several meters long and it's coiled, and this just gives us an increased surface area. The stationary phase is a solid or liquid that's coated on the inside of the tube, and that can vary depending on what type of GC spectrometer it is that you have. The mobile phase, as I said, is an inert carrier gas, so that's typically helium or nitrogen that will allow it to then pass through the column. We get the sample being injected in at the top, the components are detected once they're separated, and then we get our results displaying on a computer. So the samples are vaporized when they are injected, so it doesn't have to be a gas that we are injecting. We can inject a liquid that is then vaporized into a gas. And of course, depending on their attraction to the stationary phase, they will move at different speeds. So you can see that we've got this mixture here of the purple, pink and yellow gases, and as they pass through the column with the carrier gas, they're separating out. So the yellow will be detected first, then the pink and then the purple. So the weaker the attraction to the stationary phase, because remember the mobile phase is an inert gas, so it's not really going to be attracting the sample, so it's all to do with the attraction to the stationary phase. If it's a weak attraction, it's a shorter retention time, so it passes through the column quicker. Now, HPLC and GC are very useful for isolating components in a compound or in a mixture of compounds. The problem is they are not very good for identifying them. Retention factors can vary on a number of different factors, such as the temperature, the pressure, or even the solvent that could be used as your mobile phase. So it's not always accurately possible to identify the component. So in order for us to use these chromatography methods very effectively, in particular we use them in things like forensics or in testing for doping or testing for drug use within sport, we have to couple it with mass spectrometry. So that's why we mentioned the HMRS earlier on, the high resolution mass spectrometer. And when we combine them, we will either call it an HPLC-MS, so high performance liquid chromatography mass spectrometer, or a GC-MS, gas chromatography mass spectrometer. So how do these work? Well, let's focus on the gas chromatography with the mass spectra. The context is the same regardless of which one it is that you use. We're just going to use the gas in this case. So we're going to inject the mixture into our gas chromatograph. So you can see that we've got our A, B, C, D and E. And that's step one. Once it passes through the column and we get our different retention times and we get our chromatogram being given to us, you can see that we've got different components. So A has the shortest retention time, so it's the most weakly attracted to the stationary phase, less than probably about a minute, whereas E is probably closer to 25 minutes within the column because it is strongly attracted to the stationary phase. Okay, whereas A was weakly attracted to the stationary phase. So what we then do is each component, as they are then separated, they enter the mass spectrometer one at a time. So this all happens generally within one system that's controlled by a computer. So if we have A, B, C, D and E, they will each be entered into the mass spectrometer one at a time. So let's put our focus onto C. So once we have C passing through the mass spectrometer, we get a mass spectrum that has got our MZ values with our different fragments, and we can get this for each individual component. So in this case, you can see that C is going to have an MR of 194, and we've got different fragmentation patterns. Now, we usually will have a rough idea of what it is that we're going to have. If not, we can generally refer to a database of known substances that will have all the fragmentation patterns. And from this, we can then identify the component in each mixture. So we're coupling the separation of the mixture in the chromatogram along with the identification using the mass spectra with our MZ values, our abundances, and our fragmentations. And this can work with even very small samples of substances. In particular, as I mentioned, it's used in forensics, or it can also be used to identify banned drugs from samples from professional athletes. So when you get drug testing as a professional athlete, in particular in football or at the Olympics, every single athlete could be subject to a drug test. And if they're caught with any banned substances, then of course they would get a ban. One of the most common substances that people would get caught with would be things like anabolic steroids, because they can help with strength and they can help promote muscle growth. So one that's very common is called nandrolone, and that's this one here. And it's illegal to use this in sports because they would think it gives you an unfair advantage over your fellow competitors. Despite it being an illegal substance in sports, they do also have legitimate uses. So these anabolic steroids can be used to treat anemia, they can use to treat osteoporosis, or even different forms of cancer. So whilst it would be illegal for an athlete to take this unless they had a valid medical exemption, you may find that these anabolic steroids could be found in samples of patients with anemia or osteoporosis or cancer because they can be used as a treatment. So let's finish off by looking at some past paper questions on chromatography. So first of all, we want to know what statement of chromatography is true. So A, it can only be carried out at room temperature. B, it can be used for samples that decompose when they're vaporized. C, it can be used for non-volatile substances. Or D, it can be used to measure the amount of component in each mixture. Well, if we start with A, it's not carried out at room temperature because it's done in an oven, so it can't be that. It can be used for samples that decompose when they're vaporized. Well, that isn't what we want. When we vaporize it, we want to keep it the same component. We don't want it to compose, so it can't be B. And if it's a non-volatile substance, then it means it can't be vaporized, so it can't be C. So the answer must be D, because the whole purpose of gas chromatography is to be able to determine what each component is in a mixture. For question 2, we have, again, gas chromatography, and it tells us that the retention time is the time it takes for a compound to pass through the chromatography column. If we have a column that is packed with a stationary phase that is polar, we want to identify which will have the longest retention time. So if something is polar, what you need to remember is that like likes like. In other words, polar substances are attracted to polar substances, and non-polar substances are attracted to non-polar substances. So this is another way to say which of these 4 substances is the most polar. And hopefully you can see right away it's going to be the one that has the OH group, because OH groups give you very polar substances. So our answer must be D, pentan 1-ol. And then question 3, which of the following is the most suitable carrier gas in gas chromatography? Well, we said that it has to be an inert gas. It cannot be reacting with the compound. So water is definitely out, because water reacts with quite a few things, and so does oxygen. That leaves us with ammonia and carbon dioxide. Again, ammonia can react with quite a lot of things, whereas carbon dioxide is very inert. It surrounds us in our atmosphere and it doesn't really react with anything. So that would be our best carrier gas. And then a nice 5-mark question. In chromatography, compounds are separated because of the difference in distribution between a mobile phase and a stationary phase. Explain why this distribution occurs, and then compare the phases used in gas chromatography and high-performance liquid chromatography. So 2 parts to this process. First of all, we want to explain why there's a difference in the distribution of the compounds. And this is all to do with their affinity to the stationary or the mobile phase, or their attraction to. So the substances are separated based on their attraction to the mobile and stationary phases. Okay, so it's all to do with how attracted they may be to the mobile or to the stationary phase. And then the second part is contrasting the phases used in each. So this is basically just what is the different phases. So if we have GC, now of course you would write this out in a nice paragraph. I'm just going to draw it kind of like a table just so you can easily see. So in GC, we're going to have a mobile phase and we're going to have a stationary phase. GC, the mobile phase, is an inert gas, and you could name a specific gas if you wanted to. You could say nitrogen or helium or argon. And the stationary phase tends to be a liquid or a solid for GC that's within that column within the oven. Whereas for HPLC, its mobile phase is going to be a liquid because it's usually some sort of solvent, typically maybe water or hexane or pentanol, or ethanol, something like that. Whereas the stationary phase is a solid, or in particular, silica. So you would get 1 mark for talking about why they separate, and then 4 marks in total for explaining or stating what the different mobile and stationary phases are in GC and HPLC. So there you can see the mark scheme for those questions, and you can see exactly how the marks are breaking down. That's everything for topic 15E, chromatography. Please make sure to check out the second part of this topic, which is NMR. And if you have any questions, feel free to leave a comment below, and we hope to see you back soon.